Hello and welcome to another video on physics and graphs. I apologize for the hoodie, it's a little chilly in here, so I'm just trying to stay warm. We've been talking about position graphs one way or another for a few lessons now. So let's take what we've learned thus far and summarize it. We've seen two general shapes. We have straight lines and curved lines. A straight line means that the velocity isn't changing, it's constant. We have faster velocities have steeper slopes, slower, shallower slopes. If it's not moving, it's a flat line like so. And then if it's moving backwards, we're going to have a negative slope like this. So these are all constant velocities that are just constant in different ways. Constantly positive, constantly zero, constantly negative. On the other hand, we have curved lines, like so, where the velocity is changing. In this case, it's speeding up. In this case, it's slowing down. But both cases, they're moving forward. Next, we can talk about the velocity, how we find the velocity. The slope of a graph, change in y over change in x, is going to be your velocity. So, velocity is the slope of a position time graph. Now, if we have a straight line, we know how to find slope. We just measure the change in y over the change in x. We can literally see that. On a curved line, we can't, per se. We can say where it's slower or faster, but talking about what the slope is for a given point is really hard outside of calculus, which is beyond the scope of this class. We can say, however, like this point, this point, this point. These 3 points all have different speeds.
Or more precisely, different velocities.
Shallower or flatter section here, where if we were to draw a straight line approximating the slope at that point, would look something like this, versus the slope here, where again, if we drew a straight line approximating versus a straight line approximating, would be different. This goes back to the ice puck or the inclined plane we were looking at. Whereas the object kept moving, it got faster as time went on. And we can see that in our graph with this slope. This practice of drawing a point on a line is called drawing a tangent. Again, it's a calculus thing, but it's useful for us. If we were to imagine just this section here being the only thing we're paying attention to, and just paying attention as if it were a straight line, we can guess or approximate where it is or how fast it's going. In this case, it starts slow because the slope of this section is flatter, then it increases, and then it increases more. To restate that a different way, when you have a curved graph, it is changing speed, it is speeding up or slowing down. The flatter sections are slower. The steeper sections, the more vertical sections, are faster. Slow, fast. If you look over here, fast to slow. So, with this said, we can talk about what section is moving faster or slower comparatively based on the slope. We can actually calculate how fast something is going by using the slope. We also need to talk about the displacement. So how we measure displacement is we find 2 points on the line. I'm going to use this one here because we haven't talked about it much yet. We go, okay, we want to know the displacement between this time, and this time. Time 1, which we'll say, I don't know, is 3 seconds, and time 2, which we'll call 12 seconds. We want to know what the displacement is in that time. We just need to find out what the change in position is, which comes from our y values. This difference here is our displacement. Which, even though we're measuring y values, is our delta x. Because physicists hate you. Sorry. It's just the convention we have to get used to. So from a position time graph, like the data we've been collecting, we can and will be able to find velocity, compare different graphs, and find displacement. These are kind of goals. Let's go ahead and take a look at an example of how this might look. So back when I was student teaching, I lived about 30 miles away from where I taught. And because where I was teaching was near the city, it was rush hour traffic the entire way. I'd wake up, and when I left my house at time equals 0 here, it'd take me 2 hours to get to school. And I'd stay at school for a few hours, and then I'd come back home, and it would take me even longer because it was during rush hour. Here's the questions. How fast was I going to school? How long was I at school? When did I come home? And this graph tells us everything. We just need to work it a little bit. So let's start by talking about how long did it take me? Well, if I'm looking at this graph, right? When I'm at school, my position's not changing. I'm not moving, at least on the scale of miles. So where's the flat section? Where is the section where I'm not changing? A, B, or C? Well, A, we can look at it and we can go, okay, for every hour, I'm moving forward. So it's not A. It's probably part of my commute there. B, I'm stuck at this value here, which is 30 the entire time. B seems like a good contender. Let's check C, just to be safe. C, every hour I go on, my position decreases. It's probably me coming home. So B is when I'm at school. So how long did it take me to get school? Well, how long is A? How many hours is A? Well, we can look at A. Okay, it's 0 to 2. The difference in time is 2 hours. Simple, easy stuff. But let's talk about my displacement. What is my displacement? What is my change in position to get to school? Well, in this particular case, I end here. I start here. So my displacement, or my delta x, is always x final minus x initial. Or in this case, it's 30 minus 0 miles, which is 30 miles. Okay, this is easy, working it in. How fast? That is the immediate follow-up question. What's my velocity on my way to school? Well, I know my delta x is 30 miles, and I said my time was 2 hours. And if I'm ever uncertain about that, just trace the graph down. Trace the graph over. And there we go. So my velocity then, for section A, is 30 miles, 2 hours, is 15 miles per hour. And that might seem like a lie, but in stop and go traffic during rush hour, not right. Especially going into the city. It took me forever to get there. This is pretty easy. It's pretty self-explanatory. But it's building. B is when I'm at school. And while it might seem silly, it is still useful to go through the math for here. So while I'm at school, what's my displacement? Well, my delta x is x final minus x initial. So for section B, only paying attention to this flat section here. X initial, x final. Well, the entire time I'm at 30. So my displacement during this time is 30 minus 30, or 0. What's my velocity? Well, 0 divided by anything is still going to be 0 over the 1, 2, 3, 4, 5 hours I was there. But that makes sense. A flat section on a position time graph indicates a velocity of 0. It indicates something standing still. You're not moving if you don't have a velocity, you're just standing still. So whenever you see a flat section on a position time graph, you know that's where you're standing still. A thing you might notice here is that I don't have any directions on these, at least explicitly. In this case, the directions, only directions we have are positive and negative. Positive is in the direction we want to travel. Negative is that. We are assuming a straight line. We're assuming that the direction I'm traveling is directly away from my house. And it almost perfectly was. I could get on 90 and go the entire way to my school, pretty much. So my directions will be positive and negative. Because there is no sign here, we assume it to be positive, which is generally how numbers work. If I say I have $5, you're like, okay, that's positive $5, not question mark. If you see 32, it's not always that positive or negative. If there's no sign, we assume it to be positive. Direction in this case is positive travel and positive. The reason this matters is when we look at C. In C, I'm going home. So I want to know what my displacement is. I want to know what my velocity is. My displacement is still the difference in y. In this case, I go from 30 to 0. For this is my initial. This is my final. And I can see right off the bat my change in position or my displacement is 0 minus 30, or it's negative 30 miles. Awesome. Let's talk about my velocity. Negative is my direction. Negative is my direction in this case. So now let's talk about velocity. My velocity is still my displacement over time. In this case, it takes me 1, 2, 3 hours to get home. And I went 30 miles. That is 30 miles per hour. That is negative 30 miles per hour. Again, my direction is negative. So looking at this, I can talk about how fast I went to work. Just looking at a graph of my position throughout the day, I can figure out how fast I went to work, how long I was at work, how long it took me to get to work, how fast I went home, how long it took me to get home, and make guesses about other things. This graph is incredibly powerful. We can even go a step further. But what if we talk about, instead of between or just focusing on certain sections, let's look at random picks of time. So let's go ahead and erase this. And instead of looking at A, B, C, let's pick 2 random times. So let's say, okay, between hour 1 and hour 9, what's my displacement and what's my velocity? So first thing you got to do when you do this is you got to go on the graph and go, okay, where am I at hour 1? Well, hour 1, follow the line up, puts me here, which if I trace it over, is at 15. How do I know it's at 15? First, I can guesstimate, look at it. Secondly, if I go in 2 hours, I go 30, and half that time I should go 15. But in general, your graphs look better labeled than this. You won't need to guess. For today's argument for my ability to draw, take it on faith. At hour 9, I'm here. And without even really having to guess, that's 10 miles. So, if I were to say, be watching the GPS, but I only watch it at hour 1 and hour 9. I'm not paying attention to the rest of it. Over that time frame, it looks like I went from here to here. That's all it is, that's all I know. We could draw a line in and find the slope of that line, or we can do it slightly more mathematically. So we'll start with my displacement. What is my displacement? Well, I'm ending at hour 9. I'm starting at hour 1. So it's always going to be, always, final minus initial. Or in this case, 10 minus 15 was negative 5 miles. Negative 5 means I've just moved down the graph. That's all that means. Now that might mean I might overshoot my house and keep going negative, but as long as I'm up here, I'm heading towards my house as well. My velocity is going to be my displacement over time. So this is delta x over delta t. It's negative 5 over, well, how many hours? 1, 2, 3, 4, 5, 6, 7, 8, or if you prefer, 9 minus 1. Do the math, you get negative 5/8 miles per hour. This time will be on the computer so you can actually see the grid lines. Okay, so now we're looking at a second graph, and this graph's a little more complicated than the first one, but let's take it piece by piece. There are many more parts in this, but what we want to focus on are the same questions. So, to start, where are the sections where the velocity is constant, where the velocity isn't changing? Remember, anytime we have a flat section, the velocity is constant. So between here and here, the velocity is constant, and then here and here, the velocity is constant, here and here, the velocity is constant, here and here, the velocity is constant. You'll note that I didn't say at the corners where it bends. This is a holdover from calculus. For me, that is a point where something changes. It is not necessarily significant or is happening so fast we can't really measure it, but for the general purpose of explaining, they're there. On a real graph, one that is collected from data not just generated on Desmos, like this one is, you won't have areas like this with sharp turns. You'll have more gradual slopes, more gradual changes. For the sake of example, we'll ignore that. So we see here these flat sections. So these are where we have constant velocities. On the other hand, this curved section here, anytime you see a curve, it lets you know you have changing velocity. So we have constant velocity, changing velocity. We can also talk about where the velocity is negative or where the position is decreasing. If you're moving downward on the graph, you are decreasing your position, you are negative velocity. So here we're moving down, here we're moving down, here we're moving down. Those are the sections where we have a negative velocity. Our slope, if we had one for the curve section or in general, is negative. On the other hand, we can talk about where we have positive velocity, which is this section here, where the slope is positive and increasing. We can also talk about where we're standing still, anywhere where it's flat on a position time graph. So we're standing still here, we're standing still here. Awesome, great. What else can we do? Well, we can calculate the velocity. For a curved section, it's going to be nearly impossible, so don't do it. But on a flat section, it's going to be 0, which is just boring, so we don't do it. On each of the angled sections, we can calculate the velocity. Now, there are several ways you can do this. You can use the slope formula that you learned, or you can count. I personally like counting, but I'll do it both ways just to be sure. So let's talk about this section here between 5 and 11 seconds. If you want to do it by counting, your change in y is you're going down 1, 2, 3, 4. So that's going to be -4. And then you're going to go right 1, 2, 3, 4, 5, 6. You can pick any 2 points as long as they touch the grid and the line. I will typically go with the endpoints because it's easiest, but I could have gone to here, or I could have started here and ended here. It really doesn't matter. Alternatively, I could do it using the slope formula, which says, so I'm either going to get -4.6 meters per second, which will simplify down to -2/3 meters per second. That's for the first section, not for the entire thing overall. But that's how you do it, just counting. Now let's take a look at the slope formula. 5, 5, you can plug it in. Remember that your coordinates go over each other. So because it's 11 over 1 up, I'll just put that 11 first. And notice how the 11 and 1 are over each other. And then 5, 5, x, y goes there. If you do the math, we get -4/6, which once again simplifies to -2/3 meters per second. Either way you get there, be it calculation or counting, it doesn't matter. So let's go ahead and on your own, try to find this section.
Velocity.
You can pause after I'm done talking and give it a try. Okay, if you got -4/3, awesome. If you didn't, go back, check your math, check your counting. Let's try one more. Take a look at that last section, this upward sloping section. As a hint, you should find a positive number. Give it a try. 2 for every 1 I go over, up 2 over 1. And because it's y over x for units, it's meters per second. If you've got that, awesome. Now let's talk about displacement. Remember, displacement is just the difference in your position. So I could talk about the displacement between 5 and 17 seconds. Or I could talk about the displacement between 8 and 20 seconds. Whatever you pick something and go from there. So let's say 11 and 20 seconds. What's my displacement? Well, how far did I move? At 20, I'm at +3. At 11, I'm at 1. So I end at 3. I start at 1. Try one on your own. Let's go ahead and say what's your displacement between 8 and 13 seconds? What's your displacement? Okay, if you did it, you'll see that 8 is at 3 meters, and here you're at 1 meter, so 1 minus 3 is -2 meters. You moved, in that time frame, you moved back 2 meters. If you've got this, awesome, go do the homework. If you're not, go through it, ask questions, get a little help.